This next video is going to have us talking about motion along a line. So we've introduced a little bit of information about this, right? If we have a position equation, the velocity is the derivative of the position, right? Velocity is just how fast are you going in what direction? Rate of change of position. And then the acceleration is really just how is the velocity changing? Well, the velocity is the derivative of position, so the derivative of the derivative is what we call the second derivative. And these are the really common ones. I think the third derivative of position is called like jerk or something, but that doesn't really come up that often. All right, so again, yes, v is velocity, a is acceleration, and then just one more kind of note to talk about here. Sometimes we talk about the absolute value of velocity. That's what's known as speed. Okay, so that's speed, that's velocity after t, time, etc. A is acceleration. That's what we're going to be utilizing in this video. So we're going to start with an example. Let's call it example 3. We're dropping the ball, which hopefully is not very familiar to you, but maybe it is. A ball is dropped, and its height above ground, and we're going to be talking about feet here. After t seconds is approximated by this function. S of t equals negative 16 t squared plus 64. And I'm going to ask you a couple questions. Also, the problem is going to provide the graph. This is what the height function looks like. Now notice in Desmos, I've given it a domain. If we did not specify the domain for this function, we'd have something very silly. That says that after 2 seconds, the height is 0. That's not that silly. But it does say that after 3 seconds, we're about 80 feet below ground. And I don't know what we're dropping, but we're going to assume that the thing that we're dropping is not burrowing 80 feet into the ground. That's why domain for a lot of applications is really, really important. Okay. Similarly, if we look at like negative time, which would be like time in the past, you know, the ball came from somewhere else. Presumably I'm holding it before I'm dropping it and stuff like that. Okay. Also, I must either be on a cliff or maybe I am 64 feet tall. You don't know how tall I am. You haven't seen me in person. You've only seen me in these videos. I really could be 64 feet tall. Never know. Anyway, so, you know, this is just that there's no x coordinate. The t coordinate is the independent variable, the first variable, and that's time. And then the second coordinate is the s value, which has to do with the height in feet. All right, so let's ask some questions about this. Part A. What is the velocity when the ball hits the ground? So this is asking two things, actually. It sounds like it's only asking one, but it's kind of asking two. First off, what is the velocity? V. V is the derivative of s. And then specifically, I'm doing this thing that I hate. Specifically, it's asking about the velocity when the ball hits the ground. So I literally underlined everything, but everything's important here. So velocity, that's v. We need to find v. V is the derivative of position. And then we also need to know when the ball is hitting the ground. Let's do things one at a time. So to find the velocity, that's going to be the derivative of the position. And one of the ways that you can write this is kind of an optional step that I'm doing to re-emphasize notation. This represents the derivative with respect to t. D over d something means the derivative of that something. Sorry, the derivative with respect to that something. All right. So this is going to be the derivative with respect to t of the function, negative 16t squared plus 64. We can use the constant multiple rule, the sum rule, the power rule, all the rules to get that this derivative is negative 32 times t plus 0. So this says the velocity after any number of seconds is just negative 32 times that number of seconds. This is the slope at any point in the graph, at any t coordinate, at any input. The slope is going to be negative 32 times that time. And again, that should make sense that it's negative, right? Look at the slope of this graph. Well, this graph is always going down. The slope at any point here has got to be negative. This is a decreasing function. Okay. So it's asking, what is the velocity when the ball hits the ground? Well, this is the velocity. The ballosity. I said it again. This is the velocity after any time. So specifically, what time do we care about? It's when it's hitting the ground. That's when the height is equal to 0. Hitting the ground is when the height equals 0. And you could solve this. This would be good practice. You could solve this by saying, when is the height equal to 0 and solving it this way? Or you could kind of cheat and look at the graph. The height is 0 after 2 seconds. Good practice. All right. So that's going to be after 2 seconds. So this beautiful sentence, the red part and the blue part, what's the velocity? Negative 32t. When it hits the ground? After 2 seconds. So all that's left is combining these two things to get negative 64 feet per second. So the velocity after 2 seconds is negative 64. Velocity is a rate. All rates, except if we have like really special fancy units, like knots, for example. I don't even know what knots are, but I know that it's velocity. I mean, I don't know how big one is. I don't know how fast it is. Anyway, most rates are always going to be expressed in something per something. Miles per hour, meters per second. Here, it's feet per second. And that's our answer. That's the velocity after 2 seconds. Part B says, what's the average velocity during the fall? Well, average velocity, we know how to find that. Average velocity is just the difference in position between the end and the start and how long were we in the air. So at the end, we're at 0 feet. At the start, we were at 64 feet, negative 32 feet per second. All right, this average velocity equation is an equation that we covered in chapter 2, I believe. But remember, average velocity is just the average rate of change of position. Right, this is just average rate of change of position. That's what average velocity is talking all about. C wants to know the acceleration after 1 second. Well, the acceleration is the derivative of the velocity. Well, this is the velocity. What's the derivative of negative 32t? It's a line. The derivative of a line is just its slope, negative 32. In fact, this says that the acceleration is always negative 32. These things are negative, by the way. I didn't mention that. Negative again. Negative slopes. Negative means going down. So the acceleration is negative 32. The units are feet per second per second. Right? It's the rate of change of velocity. Velocity is feet per second. We're changing by negative 32 feet per second every second. So we usually write feet per second squared. And this is acceleration due to gravity. Negative 32 feet per second squared, negative 9.8 meters per second squared are two very common approximations for the acceleration due to gravity on Earth anyway. Acceleration due to gravity is different on other planets. Anyway, I'm not going to start talking about that, but that's basically what's going on here. So again, conceptually acceleration, right? This means that every second our velocity is increasing by negative 32 feet per second. So at the start, our velocity is 0. After a second, our velocity should be negative 32 feet per second. After 2 seconds, our velocity should be negative 64 feet per second. And every second that goes by, our velocity is increasing by negative 32 feet per second. Now, in reality, right, there's wind resistance and stuff like that. But this is how our simple calculations are going to go. Let's do one last example problem relating all of these quantities together. A particle moves on a coordinate axis where positive values are on the right. So negative values are on the left. And its position is S of t equals t cubed minus 4t plus 2. And I have a couple questions for you guys about this situation. To start, I just want you to find v of 1 and a of 1. So this is not something falling. The acceleration is not just going to be that constant for gravity. This is something moving under other circumstances, and this one's going to be moving according to a cubic function. I want the velocity after 1 second. How fast is it going after 1 second? And I want the acceleration after 1 second. How is the velocity changing? Speeding up? Slowing down? And remember, if your velocity is positive and you're speeding up, that means your velocity is increasing. If your velocity is negative and your acceleration is also negative, that also means you're speeding up. So a negative acceleration can still mean that you're speeding up. It just depends on which way you're going. Anyway, that's kind of getting ahead of myself a little bit. So to find the velocity after 1 second, we first have to find the velocity in general. Oops. So the velocity in general is just the derivative of the position function. Using the power rule, that gives us 3t squared minus 4. So specifically, the velocity after 1 is just going to be 3 times 1 squared minus 4, which is negative 1. We weren't given any units here. So v of 1 equals 1 with a negative. I'm going to make a mistake here that I see every once in a while. I want you to find the mistake. So don't write this down. The acceleration after 1 second is just the derivative of the velocity at 1 second. Well, the derivative of the velocity is 0. This is wrong. Don't write this equation down. Don't write this line down. What's wrong with this? To find the acceleration, that's the derivative of the entire velocity function. You can't just take the derivative of the velocity at a specific point. This right here is always going to be a constant. but the acceleration should be the derivative of the whole function. So watch out for that. We always have to be looking at the entire functions. We can only plug things in at the end. You have to find it for all t and then plug things in at the end. You can't plug things in before taking the derivative. Otherwise, derivative of a constant is always 0. So you're always going to get zeros in that case. So this blue stuff is the correct stuff. The acceleration's the derivative of the velocity. Derivative of the velocity is going to be 6 times t. Just using the power rule. So specifically, the acceleration after 1 second is going to be 6. So this is the answer to part A, and we're going to use this to help us in part B. Part B says, which way is the particle moving? After 1 second. Well, we didn't have units. Which way is the particle moving at t equals 1? So again, we look at the velocity. A positive velocity means it's moving forward. A negative velocity means it's moving backwards. And this one tells us that positive means to the right. So if we had a positive velocity, it'd be moving to the right. But we have a negative velocity, so it's moving to the left at t equals 1. And again, there's a bunch of different things that are going on here. Where's the position? We don't even know where it is. We haven't found it. We could find where it was. There's position. There's which way it's moving. There's how fast is it accelerating or decelerating, all that stuff. So this problem specifically is asking you about which way is it moving. Is it speeding up or slowing down? That's asking about the acceleration. And we know the acceleration is always 6 times t. And in fact, the acceleration is just getting bigger and bigger and bigger. The acceleration is getting, if the acceleration is always positive, right? The acceleration is 6. You might say we're speeding up. But we're not. Why is that? The acceleration is 6. It's positive. So the acceleration means that the velocity is increasing. But if you're moving backwards and you put your foot on the gas, all right, hold on. Maybe this isn't a perfect metaphor. If you're, I actually don't. Anyway, you're not going to speed up. I'll tell you that much. You're not going to speed up. We're going to be slowing down, right? We're moving backwards, but we're trying to start going forwards. Here's a better analysis, right? We're on a treadmill, and if we start walking forwards, we're speeding up, but our position is going to actually be slowing down because we're moving backwards. We're starting to go forwards a little faster, and we're still moving backwards for a little bit. This is a terrible explanation. The idea is that we are slowing down. And the reason, right, is because the velocity is negative, but the velocity is increasing. So velocity is negative, but getting more positive. So that means it's getting less negative. Right? You have a negative value that's getting bigger, it's getting less negative. If we were like -5 meters per second, well, if we're increasing that, then it's -4 meters per second, and -3 meters per second, right? We're getting closer to 0. We are actually slowing down, even though the acceleration is negative. All right, and that's kind of what's going on here. Let me know if you have questions about this one, specifically, kind of explained in a weird way. I'd love to talk to you about it. Maybe I explained it poorly on purpose to give you an excuse to ask me questions. I didn't, but let's pretend I did. All right. Bye-bye. Good luck.